Hey everyone, Madhav here. I am quickly giving this presentation that I did for a student design team at the University of Waterloo. It's honestly a pretty complicated topic. We're talking about how to make AI algorithms run quickly using custom computer chips. And if you haven't taken a first year circuits course and a linear algebra course, and also, if you're not familiar with, the details of how AI algorithms work, this is going to go over your head, so you have been warned. But in any case, if you do happen to meet those prerequisites, welcome to the interesting world of how to design together specialized hardware to match and optimize how we run our AI algorithms. To get started, we have to talk about, what does it mean to optimize our AI algorithms? What are we actually trying to do in the hardware that we're designing? Well, there are a number of goals which are important. Obviously, there's the cost. If we're trying to create, for example, a GPU, well, clients won't buy it if it costs too much. And the cost can be, the inferences you get, the performance you get per second, divided by the number of dollars for the chip. So all of that is like, how much are you paying for? What's the bang you get for your buck? But similarly, you can also just measure the cost in watts of energy use, because at the end of the day, the largest cost after you've bought the chip, the GPU, TPU, whatever, is the running cost of keeping the energy going. Another thing we can optimize is the flexibility of the design. For example, there are some GPUs that can support 16-bit floating point numbers and 32-bit floating point numbers. Others, they just do 32-bit floating point numbers. So depending on the precision you support, you might have a greater market and more types of algorithms can run. And another thing to consider is some chips, they only try to focus on, for example, convolutional neural networks, but not regular neural networks. Others, they might, focus on transformers in particular. Those types of chips are becoming more common. So depending on which types of, for example, precision and models you support, you might get a greater market or maybe a lower market, but your product is more optimized, your computer chip is more optimized for that particular use case. One last example is what people think of when we consider, optimizing a computer chip just to run AI algorithms. What is the throughput? How many examples can we process per second? That's just the speed of the computer chip. And this is different from the maximal possible amount of, data that can go through the chip, because oftentimes we have this thing called utilization rates in a computer chip. For example, in a GPU, if the utilization rate is low, that means there's a lot of hardware there that could be processing neural networks or something, but it's not currently being used. It's waiting for data. There's some other issue, and that's very common. So the bandwidth of our chip is usually very different from the throughput, what is actually the speed that is being achieved. So with, some of these goals already mentioned, I hope you can start to see some trade-offs. So for example, if you make a design that has support for multiple types of precision, well, that's going to increase its cost. But if you don't, that's going to decrease the cost, but the flexibility of the design will also decrease. So we have to keep this thing in mind. This is what computer chip designers always have to contend with. Whatever change they make, it's going to help in some areas, it's going to hurt in some others. And I hope that as we now move on to talking about some specific examples of changes we can make to improve our computer chips, you will think about, is this thing helping cost, hurting cost? Is this helping flexibility, hurting it? How does it affect throughput? So on. So with that, let's move on into the examples. I'm going to present different examples at different levels of detail. So by this, I mean there are some changes we're going to make that are just, mathematical changes. They're about the math behind the operations that the model has to perform. And even though we're not talking about any hardware at all, if we do math one way versus another, we'll see a difference. But at the other end of the spectrum, we can, look at individual devices, transistors, look at their detailed physical behavior and make changes there to optimize how the chip works. So at every level, we have changes we can make to better optimize our chip with these goals that we just talked about, like cost or throughput or energy. Starting off with the math then, we need to think about, okay, the math for different common types of models these days. With neural networks, you just have matrix-matrix multiplications, weights times the activations in order to get some outputs. Of course, you also have the activation functions, but that's, it's less of the total amount of computation that needs to be done. Most of the time is spent just doing the matrix-matrix multiplications, which themselves are just multiplication and addition operations. So for the vast majority of the computations that need to be performed, we're just looking at multiplication and addition in neural networks. In transformers, it's actually a pretty similar picture because you have obviously neural network layers, fully connected layers in the transformers, and then you have the special bits, which are the self-attention mechanisms. As it turns out, the self-attention mechanisms, they also use matrix-matrix multiplications, and so you're back down to multiplication and addition. So the last type of model, which is, it seems at first to be the outlier, is convolutional neural networks. Here you can see you have filters where you're, doing element-wise multiplication and then adding together the results. And at first glance, it seems like this is very different from the neural networks or the transformers. And that would be annoying because let's say, you're NVIDIA and you're trying to design a new GPU, it would suck if your GPU could either do the matrix-matrix multiplication of neural networks or transformers, or it could work for convolutional neural networks, but it couldn't do all three of them. That would really limit, the product market that you could sell your GPUs to. So how can we use math to make this more like these things so that we can make one product that just does, multiplication and addition, does those operations very well, and it can be used for all kinds of models? Well, we have a tool in math called a Toeplitz matrix. It's a fancy name, but essentially just means mathematical jiggery-pokery so that you can manipulate a convolution operation somehow to just look like a matrix-matrix multiplication. Here there is no like profound mathematical insight to be had. It literally just is, okay, we just, move this thing around in this weird way, and the end result is that the convolution that we were doing, we get the same output as the matrix-matrix multiplication. So to walk you through how this works, first, let's talk about the convolution. So in the convolution, these are filters, and the filters, each time you see one of these circles, the blue, red, gray, and red, it is showing a filter placement. So at first you have this blue placement for the filters. The first element multiplies by the first element here, the second by the second, third by the fourth, and fourth by the fifth. So you have this element-wise multiplication, sum together all the results, and that goes into the first index of the output, also in blue. Keep in mind, these are not, values. These are indices. So this is the first index of the output. It's not that, you place these filters, convolve them with these inputs, and you get out one as your final results. No. Anyways, what you can see with this convolution operation is we have these different filter placements. We know which elements are being multiplied together because it's element-wise. And from these four filter placements, blue, red, gray, red, we get blue, red, gray, red, these outputs. Well, with some mathematical jiggery-pokery, we can take all of these computations, all of the multiplications and additions, and reformulate them into a matrix-matrix multiplication. Except we have to rearrange the inputs in a special way, which is called a Toeplitz matrix. Let me give you a specific example. So with the first filter placement, we had 1, 2, 3, 4, and 1, 2, 4, 5. So first multiplies by first, second by second, third by fourth, fourth by fifth. Now take a look at this, you can call it a vector. This vector multiplying by the first blue column of this matrix. Well, the first element multiplies by the first, second by second, third by fourth, and fourth by fifth. It's the exact same multiplications that occurred in this first filter placement. And then, of course, you're summing together all those products, just like you're summing together all those products here, and you place the result in this first element of the output vector. Well, you can go through and check the other filter placements. For example, the second red placement matches up with the second column. This third gray placement, it matches up with this third gray column, and so on, such that all the multiplications and additions being run in this convolution operation are the same as in this Toeplitz matrix. And this is not, some grand discovery of math as in some, beautiful conjecture. It just is some jiggery-pokery, such that you can you can get the same output results from this format as you did in this format. Now, what's the downside here? And what's the upside here? What's the point? Why am I talking about this? Well, the upside here is that anytime we now have a convolution operation in a convolutional neural network, we can just replace it with a matrix-matrix multiplication, and we can do that in software. And because we change the math in this way, our hardware doesn't care whether it's running a neural network or a convolutional neural network, because at the end of the day, all it's going to see is a matrix-matrix multiplication. And as hardware designers, we can just optimize to make these very efficient. That's the upside. We improved their chip's flexibility um, and allowed it to, serve more types of models. What's the downside to this pretty significant benefit? Well, the downside is, as you can clearly see here, so this is the inputs. These are the inputs for the convolution. These are the inputs for the matrix-matrix multiplication. Here you have 9 numbers. Here you have clearly more than 9 numbers. And the reason is that numbers are being duplicated. So the second element, it only came once in the original input activations. In the Toeplitz matrix, it's duplicated twice. This number 5, 1, 2, 3, 4, 4 times it's repeated compared to in the original matrix. So you use more memory storage and you have more data bandwidth needed in your computer chip to transfer all this redundant data around. That's the downside. So, like with the trade-offs I just mentioned, improve the flexibility, but the cost is you're going to have you're going to have greater monetary cost as you add more data buses and more memory to store this redundant data. So that was an example of a math kind of innovation we could do to improve the goals we talked about at the beginning. Now let's talk about a software level optimization we can do, again to improve those same goals. Now this one, I hope you know how to code, because the syntax might look a little bit complicated. We're going to talk about how we order computations, how we order operations. So in grade school, you learn about BEDMAS, some order of operations for math, which tells you, okay, if we're doing this computation, we're going to need to make sure that we do what's in the brackets first, so add x and y together, and then multiply the result by w. Well, in the software that we write, in, the literal code, the functions we create, we can rearrange these computations in some ways that may be more or less beneficial. So let me give you some examples. In software, we need kernels for GPUs. In particular, we need kernels, which are just functions, which tell the GPUs what they need to compute. There's a lot of, boilerplate code here, but the key part is here. If we do the, order of operations like we just talked about, okay, we have this addition and then we have a multiplication. Well, we can create two kernels, two functions. One function, it's an add function. It just does an addition operation. This line is the important part. This is the addition operation. The other kernel, it's for multiplication. It does a multiplication operation. And the way we do it is we read X and Y from cache memory, so get this data, add them together, and then store them to the cache in this temp variable. And then the next kernel runs where you retrieve that, the sum from the cache alongside W, the weights, and then multiply them together, store them in Z, and write that result to the cache. So how can we improve upon this? If we're writing these kinds of kernels for our GPUs to know which, operations to perform, how can we improve upon this? Well, one way to improve upon this is not to think of it like, the math computation. We do the addition and then the multiplication, and, these are two separate, entirely separate operations, so they need two separate kernels. What we could try is operator fusion, taking these two kernels that perform two different operations and fusing them, merging them into one kernel in order to reduce the amount of memory reads and writes. So here's an example of that fused kernel to still compute the same operation. In this case, we're reading X and Y from the cache still, but now instead of adding those two and storing the result to a cache, we just store it in local memory. So there is no write here compared to the previous kernel. Next, we have that local variable, it's still available. It hasn't been stored to some kind of cache. So we don't need to read temp like we did before. And we still need to read, the weight W. We multiply these two together and finally write the result, the product, to memory. So now you can count, we have 1, 2, 3 reads and 1 write, compared to 1, 2, 3, 4 reads and 1, 2, 2 writes. So you can see how with the software level optimization, nothing has changed about our hardware. It's just that we are reducing the amount of memory moving about, especially the data that is being stored and read from memory redundantly. This again, it reduces our cost because we need fewer data buses and lower memory, and also it will improve our throughput, the speed at which we can operate. The downside really is negligible. We have to create some kind of special compiler to do this kind of operator fusion to create efficient kernels. But really, languages, machine learning libraries like PyTorch or TensorFlow, they already do this for us. So basically, the cost is negligible. We can ignore it. We get a bunch of benefit and no real drawbacks. That was an example of a software level optimization that helped us to better achieve the goals that we talked about at the start. Now we've done a math level optimization and a software level optimization. Those are luckily the easier out of the ones we're going to talk about. Unfortunately, from here on, more and more hardware is involved and things do get more difficult to understand because of prerequisites. However, I'll try and, breeze things along and not go too much into the low-level physics. Next, let's talk about the architectural level. The architectural level in a computer chip, we're talking about microarchitecture. Microarchitecture, I describe it as what do we put on the chip and how do we connect things together? So in this first diagram, what we're going to look at is how things are being connected together. Literally, like how do we wire together the different processing elements? That's what PE stands for, processing element. And that's where, we perform those multiplications and additions we need for matrix-matrix multiplications. So as you can see here, you have different diagrams. These different diagrams have different arrows on them, and the different arrows, they represent wires. So the collection of wires that we have to connect different processing elements together, that controls how data moves from global buffers. So that's where, we load all our weights and activations and whatnot, and how it gets to any particular processing element that needs a weight and an activation to multiply together, add on to a product, a partial sum, things like that. So the way that we wire things together, that is called the network on chip, NOC. So these are different networks on chips, different network on chips that are possible. And we're going to look at the benefits and drawbacks of different ones. So the first one that we're going to look at, we're going to call it a unicast network. What a unicast network does is it has a bunch of wires that are going to the first processing element, then fewer that are going to the second, fewer still to the third, and so on. However, you'll notice that the global buffer, it only connects to the first column of processing elements. If this particular processing element needs some data, it can't grab it directly from the global buffer. The global buffer needs to send it along, pass it along the chain, like, runners running a marathon. And the effects of this is that you can have a lot of data moving every single cycle because, each of these arrows, each of these lines is a different, it can be a different bit of data that is moving in a cycle. A CPU cycle is what I'm referring to. Here you'll count that we have, maybe 24 different bits of data, 24 wires. So there's a lot of bandwidth in that the maximum possible amount of data that can move in a cycle is like 24. It's a lot. And as we move forward, you'll see there are fewer wires. So here, we have 16. Here you have 4. Here you have just one long wire with many different heads. So out of all the designs, the network on chips, this unicast network has the most bandwidth. So why bother with these other designs? Well, you can see it in the figure. It says there's high spatial reuse, but what does that mean? Spatial reuse is the idea that when you're sending data around to processing elements, well, some of them will need the same data. So how are you going to achieve that? If you need these 4 processing elements to get the same weight, can you send it all through the one wire that, targets all of them at once? In that case, it's going to take you one cycle to distribute that data to all 4 of these processing elements. Whereas with this unicast network or the systolic network, well, the global buffer passes it on to the first processing element, and then the first passes it on to the second, second to the third, and third to the fourth. So you're going to need 4 CPU cycles, clock cycles, in order to get that data that everyone needs to everyone, to all the processing elements. So this is why we describe this as having low spatial reuse. You can't distribute data quickly across space, across different processing elements. And these architectures, they have higher spatial reuse because in this case, the bandwidth is 4 arrows, but each of these 4 arrows, it connects 4 processing elements at once. In this case, the bandwidth is just 1 bit because one wire, but the wire links every single processing element. And that's why we call this a broadcast network. It's like that 1 bit is, it's needed across all the processing elements. So you're broadcasting that data everywhere. You're just sharing it all over the place. So low bandwidth here, high spatial reuse, high bandwidth here, low spatial reuse. And one question that I didn't answer here is, why would you need to distribute data? Why would you need to reuse data? Well, for that, we can just, look at how for example, the CNN works. You have, as you can see, this one filter being applied in multiple positions. So these same filter weights, they're applied to different regions of the input activation. So the same weights, those same numbers, that same data will end up multiplying different input activations. Well, that's why it would be good if you could, for example, distribute the same weight here. And you saw that CNN filter had four placements. Well, distribute that same weight. You have spatial reuse there. Distribute different input activations to the different processing elements, and that allows you to avoid having to spend four cycles sending the different inputs, and then four more cycles sending the different weights, well, the same weights to different processing elements. So that's an example of an architectural choice where we change the microarchitecture, we change how things are connected in order to either prioritize bandwidth or spatial reuse. And that depends on, the kinds of architectures we want to support, our end requirement. So with that being said, I'm not going to dive deeper here, but this is basically, where the vast majority of hardware optimizations go in, which components you include, how they're connected, this involves the kinds of memories you're using, the way that you process data, what the insides of those processing elements look like. They're not just black boxes. Something has to go in there. But because, I don't have years, I can't talk about all of it. So we're going to move on. In these next levels, I'm actually going to avoid going into much detail. I'll basically hint at things for any electrical engineering students that are interested, but I understand that not everyone has that kind of background. So just a quick hint, when you're talking about gate level design, you have different gates that are possible. You have, NAND gates or NOR gates, AND gates, OR gates. What do you use? If you've taken a first year circuits course, you might have heard the term De Morgan's laws. These are just laws that tell us, sometimes to achieve a goal, we can substitute one gate for another, perfectly substitute. And this gives us flexibility as designers so that we can choose which type of design we go with, which type of gate we use when we're creating circuits like, let's say, multiply accumulate units or multipliers, adders, things like that. Well, the quick version is we want to use NAND gates a lot, a lot, a lot. But the more complicated version is that, different gates, they can they can have different propagation delays, how much time it takes for the input to change the output, how much time it takes for the gates to do their jobs. They can have different sizes. They can consume different amounts of energy. And so there are different styles of design to even implement, like a NAND gate. When I say, hey, let's use a NAND gate, well, yeah, that's true if you're using something called complementary static gates. But there are other architectural styles where, for example, you can get the functionality of both a NAND gate and an AND gate at the same time. So really, there's a lot of complexity here that is hidden behind these symbols. And if you ever look at transistor level design, which are the transistors that are connected, say, to enable this to turn into this. Um, with some styles of designs, you're literally adding an extra gate to go from a NAND gate to an AND gate. In other styles, you can get both at the same time. There's not much overhead, but the design is complicated, and you have to make sure the transistors you're using are sized right. So, anyways, if you're interested, comment, and I can answer some questions or provide some resources on it. But yeah, there's a lot of detail-oriented optimization you can do with the gate level as well. Device level, we're just going to ignore because way too much complexity to talk about to a general audience. But that does it for some different levels of optimizations to achieve our goals in creating, more performance, more cheap, more flexible, and higher throughput, faster computer chips. And what I really like about this field is that you can learn about these different levels, and then you can specialize in the level that you're interested in. And so there's honestly, room for everyone from mathematicians to like detail-oriented electrical engineers to, compiler engineers that are just, interested in software. All sorts of people to work at different levels of detail, different levels of tangibility to improve the same goals. And that makes this discipline quite interesting, intellectually speaking, in terms of the challenges you can resolve. So I hope that was a nice intro. If you're interested in learning more, check the description and I'll leave some notes.